a top executive at the heart of Google's DeepMind efforts to advance artificial intelligence, joins us right after this. Welcome to Big Technology Podcast, a show for cool-headed, nuanced conversation of the tech world and beyond. We're joined by a very special guest today. Colin Murdoch is here. He's the Chief Business Officer at Google's DeepMind. We're going to talk a little bit about theory. We're going to talk about practice and how Google is trying to take the cutting edge in artificial intelligence and productize it. Colin, welcome to the show.
Alex, it's fantastic to be here. I'm really looking forward to this conversation.
Great. So would you like to start easy or hard?
Wherever you like, Alex. Let's jump in.
Let's just jump in. Why build artificial general intelligence? I mean, this is something that is a stated goal of DeepMind, to build AI on par with human intelligence, or even something that surpasses it. Why do it?
That's right. Well, I mean, just stepping back for a moment, I think it's really important to think about what artificial general intelligence is, or AGI is, because you'll be familiar with a lot of AI systems today. You build an AI system to solve a particular problem, and that works exceptionally well. And we've seen huge kind of breakthroughs in fundamental AI research, which has driven really important impact in the world through this form of AI. What we hope, though, with artificial general intelligence is to build a system that can solve multiple different problems. So one AI system that can solve multiple different problems. And much like us humans, Alex, that means we can take learnings, and the AI AGI system can take learnings from one setting and apply it to a new setting. And we expect that, therefore, means that this AGI system can create more creative and transformational solutions. And we know this is possible, actually, because humans are a form of artificial, or not artificial, in fact, real general intelligence. And look at the incredible things that we've been able to achieve. And that's why we at DeepMind think it's a really worthy pursuit to develop a form of artificial general intelligence that will help hopefully tackle some of society's biggest challenges, things like climate change and problems and questions in healthcare. That's actually the core of what we're up to, and it's incredibly important and I think incredibly interesting.
Yeah, but it's going to do more than just that. I mean, you can direct. I'm sure you can direct it to do climate work and healthcare, but there's a whole host of different things that an AGI will I imagine will be able to do. From your website, you say by building and collaborating with AGI, we should be able to gain a deeper understanding of our world. So that's even a level deeper than you just mentioned, resulting in significant advances for humanity. How will this technology, A, provide a deeper understanding of our world, but B, if we can apply, if it can think like a human, then how practically will it be able to achieve some of these, goals that you just discussed?
So I think the application in science is a really interesting area to think about. Science is an incredibly complex area that we as humans over the years have made incredible advancements in. And those advancements in science have really enabled us to build the societies we have today, have the health that we have today, have the food production that we have today. But at some level, it feels like we're meeting the limits of the knowledge that humans alone can create through this process. And a concrete example of this is proteins. They're the building blocks of life. They're what makes you and I work, Alex, right now. If we didn't have proteins, the little machines in our bodies, we wouldn't function. And scientists for years have been trying to determine the structure of proteins, actually, because if they go wrong, if they're misformed, if the structure isn't quite right, then that can cause things like disease and all sorts of maladies across a whole range of different areas. The challenge is for humans, we've been trying to do that using experimental means. So it takes years of painstaking research and millions of dollars of specialist equipment to determine the structure of just one of these proteins. Which is why actually experts for about 50 years now, actually, these are really advanced scientists, have been trying to use computational approaches to determine the structure of a protein. Because proteins are made up of these little units that are encoded for in our DNA. And we actually know the sequence of those units. The challenge is, how do they turn into this three-dimensional structure? So there's a really important problem there. There's the core of a lot of really important biology understanding that we've not been able to solve as humans. And this is a good example of where AI has been able to step in. And I can tell you a bit more about that.
You're building up to. Yeah.
AlphaFold. AlphaFold, bingo, yes.
I mean, so I'm going to, wait a moment, because So AlphaFold, we're going to talk about it more in the second half, but you've been able to decode proteins with DeepMind research using this AlphaFold system. But that is still a narrow intelligence. So you're actually taking it a step deeper if you're trying to build an artificial general intelligence. So talk a little bit more about why that's necessary.
Well, there are many problems that we're able to uncover and begin to solve with things like AlphaFold. But if you step back and think how humans, we solve problems, we come across one problem, we solve that, and that typically opens up a new problem. And if you step back and think about the universe as a whole and our world as a whole, the size and the scale of that problem space is immense. And I suspect there are problems that we've not even thought of today. And I hope with a system like AGI, artificial general intelligence, is that once we solve one problem, that typically opens up and shows this kind of branching set of new problems. The AGI system will be able to kind of translate across that problem space at a speed and scale that we can't even imagine today. And in many ways, it's a hard question because we're bounded by our existing human intelligence. So we're bounded by what we currently know. But if we can build a system like this, I think we'll be able to explore this problem space in an exceptional way. And the reason why I used AlphaFold as an example is because I think science and scientific discovery is actually a really fascinating and important area that is this kind of endless set of problems that we hope an AGI system will, working with humans, be able to help us crack.
Doesn't this cede a lot of control or a lot of the sort of meaning of what it is to be human to the machines?
Well, what we see actually in AlphaFold as a good example, and even when it gets to AGI, is that we'll see computers and people working together. The great example that actually from a couple of years ago that still resonates for me is a system called AlphaGo. Now, Go is a board game which is very popular in some parts of the world.
I think our listeners are familiar, but yeah, you can go ahead.
Yeah, fantastic.
Yeah.
And people studied this for thousands of years. And we developed an AI system that was able to play AlphaGo. And we set it against various human experts. And, in some cases, the human experts won. But over time, actually, AlphaGo became increasingly powerful. What we discovered, however, was that once we then made AlphaGo more generally available, the humans actually used AlphaGo to improve their performance. And that's often the case. So the AI systems help the human improve, and you put these two things together, and in many, many cases, it's the AI system plus the human that ends up being the most fruitful, the most powerful outcome. So there's definitely a path there, I think, of a sort of co-evolution or co-development between these two forms of intelligence.
Yeah, but again, these are narrow intelligences, right? They are built for one specific task. So when we, if we're able to achieve an artificial general intelligence, which is basically going to be able to think and sort of perceive the world and plan on par with human, obviously it will exceed human because it can have the entire power of computing behind it. We're limited by our brains and we get tired. That's much more powerful. I mean, don't you think that's like a completely different level? And again, like, we talk about a partnership, but what's there to say that we're again not? I mean, it does seem like there's a point where the machine will just like not need the human feedback to make these discoveries. So that's the question: are we going to cede a good chunk of what it means to be a person, to be a human, to these machines? And if so, maybe that's good. Maybe it evolves humanity to a different place. But yeah, what do you think about that?
Well, I'm certainly excited to imagine how an increasingly capable system will help humanity and also help humanity expand our capacities. I mean, one way I think about it is that, I've got 3 children. I'm an adult, so I've been around longer for them. They're a form of artificial general intelligence, so am I. But we can work together. Even though I happen to know more than my children, we can work together. They sometimes teach me things that I'm surprised of as well. So I think these are different forms of intelligence that I hope can work together in harmony in many ways.
So it's interesting that you mentioned your children. It's almost like creating new life in some ways. Should the entities being responsible for creating this new life in some way be businesses? I mean, should we have businesses trusted with the stewardship of this new, fascinating form of intelligence? Should we reach it there? And if so, why?
So I think the way I think, rather than life, I think the way I think about it as a tool, I think that's probably the framework I use when I'm thinking about these sorts of technologies. And then I think as we think about building these really powerful and important tools, then I think businesses do have a really important part to play, for sure. I think government has a really important part to play. I think regulation has a really important part to play. I think society has a really important part to play. This is a new technology, a new set of tooling that's going to have a really important and positive impact on the world, and one we've got to develop in a responsible way, because it is a very powerful technology. We've got to take great care of it as well. So that is why actually at Google DeepMind, we have, and it's always been part of what we do, this kind of responsible approach, or pioneering responses, as we call it. It's always been in the DNA of what we do. I think all of these actors need to work together in harmony, actually, to develop something that's really important and impactful for society.
Yeah, but you did just compare the intelligence to, it's a tool, but you also compared the intelligence to that of humans. So it can't be both of those things, or maybe it can. It seems like in some ways we're like both, it seems like we're both in awe of like what these things can do, and still not fully in comprehension as a species of what we're working on. Do you think that's a fair assessment?
I think we're at the early stages of a very long ladder, if you like. So we're on the first rung, and predicting exactly where research itself will go is always a precarious task. I'm very hopeful, if that's what you mean by an awe, of the potential for this technology to really help lift humanity to new levels, to help things like climate change, to help in things like health. I think that's really important to keep in mind. We've got to continue to interrogate these systems, to understand how they work, to make sure we're doing it in a responsible way, to make sure we get the right review in place each step of the way, so that we do understand, we do roll them out in a way that makes sense for society overall. Then we've got to do both those things. We're going to be bold in how we develop it, but also responsible and take care.
Okay. So let me ask you a little bit about what the path is to getting there, right? So you talked about how a general artificial intelligence will sort of be able to learn and apply lessons from different fields or different areas of experience. So what type of research and advancements need to happen in order to get us closer to that point?
Well, we are still in early days, but let me give you some examples of what's currently working, what we call generalization, and I can talk about some of the areas of active research we think are going to need for us to get there. So just stepping back for a moment, what I mean by the ability to generalize, and you'll hear this term a lot in this field, is the ability to take learnings from one setting and apply them in another setting. And we recently developed, for example, an algorithm called mu0, which was originally developed actually to play the games of chess and Go. And then we realized we were able to take this algorithm and apply it to, I'm going to say the game of YouTube video compression. Now, it's maybe funny I say that, but we were able to take an algorithm developed for games that was a master in chess and use that to dramatically reduce the bandwidth requirement to stream YouTube videos. And we did that by understanding that actually a video is a series of individual pictures. And if you imagine the transition between each of those pictures like a step in a game, that gave us the insight that this algorithm would generalize from playing chess and Go to YouTube video compression. Another example actually is an algorithm we call Flamingo. And we were able to use Flamingo as part of an app called Lookout, which is an app developed by Google. If you're partially sighted and you need help, you can use your mobile phone to take a picture of something, and then you can ask Lookout what's in that picture, and it can help you, can kind of be your eyes. And we realized that algorithm could be used and redeployed and generalized into adding the descriptions into videos that are uploaded to YouTube Shorts. So creators creating videos on YouTube Shorts, they have less time, they upload the video. The algorithm that helps people find those videos needs something to go on to help people discover them. So we discovered Flamingo was also able to look at that video for you, essentially watch all the videos for you and add data, metadata to those videos, such that when you're searching for those videos, it's much easier to find the videos that you need. And when you consider billions of videos that are viewed every day on YouTube Shorts. That's really significant. So those are just, I'm calling those out because those are two examples where we're beginning to see these forms of generalization. And of course, generative AI is actually a great example as well. So these new tools where you're able to interact with them in a way that is kind of fairly conversational and get a really surprisingly and powerful response. So that is one way we're beginning to see this move towards more general intelligence. And maybe I could just jump in and tell you a little bit about how, for example, that recent work in generative AI is allowing us to move closer to AGI. And then I can tell you a bit more about some follow-on research.
That's fascinating.
Yeah. Fantastic. So what's maybe surprising to know, if you've been following the field in generative AI, you've really seen it burst onto the scene in the last 18 to 24 months, is that some of the underlying breakthroughs were developed maybe about 5 years ago. What's happened in the last 18, 24 months though, is these systems have been really, really scaled up. And by that I mean the size of the model, the number of parameters in the model which contain the model power has grown dramatically. And these systems have been trained on kind of larger and larger data sets. And what's happened is that by scaling up these models, we've seen these emergent capabilities appear. And by that I mean it's not always possible to predict exactly what capabilities will appear, but we've had these new capabilities appear that have demonstrated really powerful generalizability. So you can then take a system that's been trained in this way and you can ask it to summarize a document or write you an email. And it wasn't necessarily trained expressly on these tasks, but it's able to achieve these tasks because of the training process and the scaling up that's happened. And that's been, as I'm sure you've been following and many others have been following, that's been a massively important breakthrough in the last 18 to 24 months. But these systems are still not complete. They still get things wrong. They maybe can't plan in the right way. They maybe can't remember what you did yesterday and help you today. So things like memory, the ability to remember between episodes, planning, the ability to imagine a whole range of different future scenarios and plan effectively in that setting. Those are two areas of active research that are really important. And at a kind of zoomed out level, another is what we call kind of concepts and transfer learning. So as humans, we're able to build this kind of deep conceptual understanding, and that actually forms a kind of really strong foundation for us to take knowledge that we generated in one setting and transfer that to another. So concepts and transfer learning, planning and memory are all really active areas of research, which I think will help us push the next frontier. And actually, by the way, we haven't necessarily reached the limit of making these models bigger either. No one's quite sure where that limit is. And so that's also a really important active area of research, just making these things bigger and bigger. Where will that go and where will that land? And what more can we get from that?
Yeah, we've had Jan LeCun on the show, and I've been speaking with Jan since 2015, 2016, so 7 or 8 years on this point about what intelligence is from the eye of an artificial intelligence researcher. And he's always said that it's the ability to predict and to plan. And it is very telling right now that the research now is all about teaching these AIs to predict and to plan. And in fact, speaking about the new Gemini model, I'm pretty sure people from DeepMind have talked about, I think I'm going to just cite this, that the algorithm should be better at planning and problem solving. So that seems to be where we're going. So first of all, I'm going to get, I have a few questions for you about Gemini, but just to talk about it on a broad level. How do you teach an AI to plan and predict?
So there's a whole range of different active research tasks here. And to be clear, there isn't an answer yet, which is why it's still active research. But one of the ways we motivate this research is by making sure we have tasks that require planning. So we spend a lot of time and investment in building a whole suite of different evaluations and tasks, which then provide the target, if you like, for our research and our research programs to focus on. And that's a really interesting definition of intelligence. And one of the definitions of intelligence that we use at DeepMind, and was actually created by one of the founders of Google DeepMind, Shane Legg, is intelligence is the ability to perform well across a range of different tasks. And I really like that definition because I think it's very descriptive, and it's very easy to operationalize into a research program. And so this sense of building multiple different evaluations and tasks that provide then a way for us to measure our performance and progress against whether it's planning or adding memory is really central to actually the way we conduct research. And then behind that, it's a creative process. So what you're trying to do is bring together people from a whole range of different disciplines, from neuroscience, from different areas of AI research, to come together and have ideas about how we could make progress, and then use the incredible engineering talent we have and the compute resources we have to experiment and take steps forward. That's how we do it at a kind of meta level.
And DeepMind started largely with some breakthroughs in gaming. So how is that applicable for it? Because I think about predicting and planning, and it seems like if you're playing sophisticated games like Go, then that's basically going to take you in that direction.
Yeah, it's a great point. It's because games are a fantastic proving ground for these algorithms. They're fantastic because they're actually hard for humans. They have ability for us to measure how good performance is. There's normally a score of some sort, so we can benchmark the algorithm's performance versus the human's performance. And there's a whole raft of different existing games out there that can push and pull the algorithm, the AI's capability in different directions. And by the way, you can develop new games. And I think maybe the final point is that games can run faster than clock time. So you can do many iterations in a kind of simulated game much faster than you could experiment in the real world, which is why there's such an incredible proving ground and development ground. You're absolutely right for these algorithms. And we continue to invest deeply in kind of game-like environments for exactly those reasons. And maybe one other important point, they're also a really useful way of testing algorithms out to test kind of their limits, and we can check their kind of technical safety to make sure they're doing what we expect them to do. So they're a nice way of developing and testing an algorithm before they break out into the real world. And maybe a nice example here, actually, we often use this technique of first developing an algorithm in a game, to your point, to do planning. And there's an example here in robotics. If you try and train an algorithm directly on a real robot, it's going to take you a long time because a robot can take quite some time to complete the task. And in the beginning, it may be all over the place, maybe like a young child learning to walk. What we do is we create a simulation of that robotic environment, be a robotic arm stacking blocks. And we train the algorithm in that simulated environment until it gets good in that simulated environment. And we take the algorithm and then we apply it to the real robot stacking blocks. And we discover it's actually then pretty good out of the blocks. And in the real world, the robot can then begin to build on the training there.
So the way that I picture this happening is like, it feels like most of the general public has started to get a chance to start talking with AI via these large language models. So, when I try to conceptualize what this might look like down the road, I start thinking that when I'm speaking with ChatGPT or a Bard or a Bing, it starts to remember who I am. It starts to be able to accomplish tasks for me. It starts to be able to help me plan. Is that sort of the next step here? Is that where this research is building toward?
That's right. So you're able to converse with these dialogue agents today, as you've discovered, and you can have actually quite a meaningful, important conversation. But it might have not remembered what you did last week, for example. They've got limited kind of context windows, as you may have heard it called. But what you really want it to remember, as you've noted, what did I do yesterday? What did I do last week? What's my preference when it comes to kind of looking at a given film, for example? Because next time I ask to watch a film, it wants to know what I watched before and maybe what my preferences were. So that ability to remember more about our previous interactions actually becomes really important.
These things have the memory of a goldfish. It's like you're talking with it, and then 5 minutes later, it's like, hey, just remind me what you said. It totally forgets. So that's one step.
Yeah, absolutely right. It's a really important area for us to kind of expand the memory of these systems. Sometimes we refer to this as episodic memory. So they remember important episodes in the past, so they're able to bring to bear that important understanding. And then when it comes to planning about the future, these systems need to be able to stop and reason about the right sequence of steps to take. So, for example, I want to plan a holiday. I want to go here, then I want to go here, and then I want to go there. And the series of things I want to do may change over time. I may get on a flight. If you could ask one of these systems today,
I didn't catch that.
They can come out with a pretty good response on some of these things, but they aren't able to plan based on what you've done in the past, and what would a reasonable kind of itinerary be that's changing over time. I'm actually going to holiday with my family very soon, so this is very live on my mind. And I don't think the AI systems can really get to a level that I would really want them to at this point.
Right, and so we think about where this is going. We talked a little bit about being able to predict and plan. We talked about we sort of hinted at multimodality, right? Like having a model that's generalized, so being able to like do text, but also like a human, we can talk, we can read, we can see, we can process, and most of these models have just been text or computer vision or computational. And it does seem like the next step is really going to be bringing them all together. That seems like a massive technological feat. But my understanding is that is something that's being worked on inside Google with this new Gemini model. I mean, those two descriptions that I just read are both Gemini. So talk a little bit about what Gemini is and how it's going to take us on that road.
So Gemini is one of our latest research programs, and you're absolutely right. One of the really important areas it's touching on is what we call multimodality. It's a bit like the human senses you just described. We can kind of use all our human senses together and combined to achieve the goal we're setting out to. So it will bring in things like text. It will bring in things like images. And it will be able to input those things, but also output both those things. So you might have a question about something you can see. You can share that image, and you can also ask a question about it. You may want to then adapt something in that image by saying, please edit this element of the image, and it can do that for you. So bringing together these different modalities is something that is a really cool and important part of that Gemini program, as well as the kind of memory and planning architectures that we discussed earlier. And maybe a final important component is we're hoping to develop models of different sizes and scales, so there'll be kind of different sizes of these Gemini models, which can then be applied to different use cases depending on what's important.
I mean, has there been anything about training Gemini that surprised you, or is this kind of like where you think it's supposed to, it should have been going the whole way?
I'm not deep in the Gemini research program myself, but what I would generally share is that it's not Gemini specific, is that when it comes to training these large models, I think people in general have been surprised that as you make these models bigger, they get more capable and they start to demonstrate these capabilities that you wouldn't necessarily have planned or expected. And in the field, this is generally referred to as these emergent capabilities. Mm-hmm. And I'm not sure if we fully got to the end of that process yet. So there's a kind of almost a constant state of surprise as these new capabilities emerge.
Right. So I was speaking with some folks at Google and trying to figure out like what to ask you about, and someone brought up talking about modes of training. So I'm curious, I want to ask you about the DeepMind approach versus this new approach that's, or maybe not new, but definitely is gaining share in people's minds, called constitutional AI. So I'm just going to read you what constitutional, and our listeners, what constitutional AI is from a recent New York Times article. And I want to get your take on whether that's the right way to train these models. So it says, constitutional AI begins by giving an AI model a written list of principles, a constitution, and instructing it to follow those principles as closely as possible. A second AI model is then used to evaluate how well the first model follows its constitution and corrects it when necessary. I'm curious what you think about this this approach, and whether that's something that Google would consider employing, and if not, why not?
So this is kind of I would generally think about this approach and the other approaches like this as a way of ensuring these models are behaving in the way that we want them to behave. And we do definitely think about that very deeply. It's very important to everything we do. And there are different ways to do that. One way is actually by having an AI system like the one you've described provide feedback to the model that you're training about whether it's behaving in the way that the designers would like that system to behave. And that's certainly something, it's all part of the overall approach. Another important way, actually, is that you have humans providing feedback to the model. This is a process called ROHF that folks may be familiar with, where human raters interact with these models and observing the constitution and provide feedback to the model on whether and how well the model is performing against that constitution. And actually, at the moment, that's a really important part of, I think, the core research process, because humans are actually very good at this. And there's a kind of secondary benefit of that, is that we are beginning to understand how we can begin to embed more and more human feedback into the model process. So I think in general terms, yeah, this is a really important part of how we approach research to make sure the model is well aligned with the sort of, if you like, constitution that the designers and the society ultimately would like these models to be behaving in accordance with.
One last question for you before we go to break. Why does everybody in this field, or some of the leaders in the field, just constantly compare this work to the nuclear weapon project? I mean, I can't go a day without hearing an AI luminary talk about how, like, they're the next Oppenheimer, for instance. I mean, this is from a New Yorker story where Sam Altman said, let's see, he compared the company to the Manhattan Project as if he was chatting about tomorrow's weather forecast. He said the U.S. effort to build an atomic bomb during the Second World War has been a project on the scale of OpenAI. And he just tweeted that he was hoping the Oppenheimer movie would inspire a generation of kids to be physicists, and sort of missed the mark on that. And he wants, a new movie of that scale. Basically, put me in a movie or something of that nature. Why? What's going on with all these comparisons?
So I've not seen the Oppenheimer movie yet, but I'm looking forward to seeing it. I think the comparison that I often hear is actually of the Apollo project, the space project, and I think the reason examples like that Apollo project
you don't hear these nuclear comparisons. I feel like they're all over the place. I don't hear anyone talking about this as a space project.
Well, maybe I hear it more because that's actually how Google DeepMind, we often think about it and talk about it. And I think the kind of fundamental first principles analogy is that these are projects where you're gathering together a large group of very, very talented people with a very clear focus and a common belief. And if you can do that, then you can make incredible progress. I think these sorts of projects are maybe kind of offering that sort of inspiration to folks working in this area.
Colin Murdoch is here with us. He's the Chief Business Officer at Google DeepMind. When we come back, we're going to talk a little bit about the business side of these models and especially how they're being applied within Google. Back right after this. And we're back here with Colin Murdoch. He's the Chief Business Officer at Google's DeepMind. Colin, what is the state of the merger between DeepMind and Google Brain, which just came together to sort of be able to work together in a way that hasn't happened for years?
That's right. So we've just formed Google DeepMind from the team that was at DeepMind and the team that was at Brain. And actually, these teams have been working together for quite some time in the background. I think the recent merger, if you like, to form this super unit has come at a really important time in the overall development of AI. We're kind of in this super era or golden era of AI development. And we just thought it was the right time now for that reason to start to bring together the talent, but also the compute and the resources so that we could make sure we were focused and organized in the right way for the next phase. And I've actually been at DeepMind, now Google DeepMind, for about 9 years. And the pace and the change and the kind of frontier that we're working at means we're constantly needing to refine the way we organize to make sure that it fits where we are in the kind of technology evolution cycle. And it's going great. I'm really enjoying kind of getting to know the entire new team, and we're making good progress.
Right. And so it's so interesting because, DeepMind's areas have been gaming, working on protein folding, which we're about to talk about. Google Brain, maybe more search related. So how much of your activities are now going to be focused on the core Google business versus some of this other type of research?
I think what's interesting to know, even at DeepMind, and actually this is very close to my role, is that we have for a long time been taking the technology that's been developed in our fundamental research programs and apply that to Google's products and services. So that's actually been a cool part of both these groups, and actually is now a fundamental part of what we do at Google DeepMind. So we're both advancing the state of the art in the technology, applying that to really big problems in science, and then using those breakthroughs to drive value and impact across these, what was often billion user products at Google. And that's absolutely right, Alex. It's fundamental to the new setup at Google DeepMind.
Mm-hmm. So where do you see the bigger business opportunity? Is it going to be, you're the chief business officer, so is it going to be search? Or we talked a little bit about artificial general intelligence. You have AlphaFold right now that's out in market. Like where's the future of the business on this front?
So search is, of course, an incredibly important part of Google's portfolio. I expect it to continue to be a very important part of Google's portfolio. So we'll continue to do everything we can to drive value in search. Let me tell you about how I think about it, because this is a technology transfer process, and that's not easy, going from research to real world impact at any means at all. Even when you're operating at kind of Google DeepMind, working with Google, I think about it actually as a matching process. So on the one side, we have all this amazing research and these research breakthroughs, and there's a team of people that are developing those. And on the other side, we maintain relationships with all the great businesses and business units across the whole of Google, and in fact the Alphabet group as a whole, so we can deeply understand what's important to them in moving their business forward. So we've got this set of solutions on one side and a set of problems on the other side. And then we try and match these two things together. I sometimes joke it's a bit like running a dating service where you're trying to match problems and solutions. So we go ahead and do that, and then we try that out, and if it works, we go ahead and launch. So there's a process there. That's what I want to share. It's quite important to share. There's quite a systematic process, and it's one of matching technology solution and product problem as defined by the business. Search is an important area. We've done a lot of work with YouTube as well. So, for example, I talked about that a bit earlier. We've worked with YouTube to help create better tooling for YouTube Shorts, so you can more easily find the videos you want. We work with YouTube to reduce the bandwidth requirement to watch these videos. We've even worked with internal teams to create better coding tools, so we can kind of really power up all the developers at Google. We've worked with other teams at Google to do things like predict the output from wind farms that Google is part of, so we can make more efficient use of energy. So there's a whole range of different applications, and I think that's important to recognize. Yes, search, I think, will continue to be really important, and also I expect us to kind of weave the technology into all parts of Google, so we can really help lift the whole business.
Yeah. So talk a little bit about your process between taking, a research breakthrough and then actually putting it into production.
So it starts in the kind of research setting. We have a group of researchers that are working towards ultimately artificial general intelligence. And as a result of that, they're developing all these new algorithms and breakthroughs along the way. We have a dedicated team of technical specialists and product managers who are constantly tracking that evolution, this kind of gold mine, if you like, of research breakthroughs. And then those same people are also in constant contact with the business owners, with the product owners that sit across the Google and Alphabet ecosystem, deeply understanding their world, deeply understanding their priorities and the problems that are important to them, and trying to find a way of casting those problems in a way that match up with the algorithm that has been developed in the research process. The example I mentioned earlier actually is probably a good one. So mu0, this algorithm was originally developed to play games like chess and Go. Person in this team was talking to the YouTube team, and they were talking about how it would be valuable if they could reduce the size of a video, because it could be streamed to more people in more places around the world. And it's not immediately obvious to anyone that an algorithm developed to play games of chess and Go can then be applied to reducing or compressing a video. This is where the really creative component comes in, because they realized if you think about a video as a series of images and steps in a game, and in steps between those images, you can think about that as a game, with each kind of picture in the video as a stage in the game, and each step between those pictures is a step in the game. And so that was enough intuition for them to go, well, why don't we try mu0 on video compression? So that starts the conversation. That's the initial kind of matching phase. The next step is to take that algorithm and work with the product team, in this case the YouTube team, to take some videos and try it out. Try it on real data. Because it doesn't always work. It's a hypothesis. We run a portfolio here of these things, and some of them work out and some of them don't. So that's the next step. We used to call it incubation. We kind of still do. And the final step is that if it works and if it meets the bar, importantly, of the product team at Google, then we work with them to help make it launch. So we start at the beginning with a matching process. We then kind of incubate and prototype. And then finally, if it works, we go ahead and launch. And that's a kind of individual project. But zooming out at a portfolio, we have this kind of constant humming and rolling portfolio of these projects to make sure we've got this flow back and flow forward of innovation between the two areas.
Cool. So why don't we talk a little bit about, we have about 10 minutes left, so I want to talk a little bit about how this works in a couple areas. I definitely want to cover protein folding, which is I think the most interesting breakthrough that DeepMind has come out with to date. And then maybe we can end on self-driving cars. But let's start with protein folding. I think that AlphaFold, and maybe we've done it earlier in this conversation, sort of gets talked about as sort of a thing that exists, and okay, it happened, and then people move on. But I actually want to hear a little bit about what is going on with AlphaFold. Talk a little bit about the breakthrough itself and how it's being applied right now.
Fantastic, yeah. So we did touch on it earlier on, but just as a brief recap, AlphaFold is a way of determining the structure, the 3D structure of proteins, which ends up being really important in a whole range of different fields. And this is something that folks have been trying to do for many years, but took years to determine the structure of just one protein. But with AlphaFold, we've gone from years to minutes to even seconds sometimes to determine the structure of a protein. So what does that mean in practice? Well, we've used AlphaFold now to map all 200 million proteins known to science, or 200 million proteins known to science, and we've made that available to everyone. And actually, someone estimated recently that that's probably saved about 1 billion years of PhD time. Because you probably on average you spend about a PhD to determine the structure of just one protein. That's available to everyone now. We've had hundreds of thousands of biologists and scientists from around the world that are now tapping that database to be able to advance their particular work and their particular domain. Let me tell you some stories about how people are using this. There's actually a team, I think at the University of Colorado, that are using AlphaFold predictions as part of their work. So they're focused on the problem of antibiotic resistance. We kind of take antibiotics for granted in most parts of the world, and that's a great thing. But the bacteria are developing, and there is increasing cases. I think in the US alone, there is probably millions of cases a year of antibiotic resistant diseases. And that's an important, also quite a scary problem. So there's a team of scientists working on how to address antibiotic resistance. There's a particular bacteria involved in antibiotic resistance, and they've been trying to determine the proteins on this bacteria for a number of years, quite some years, but hadn't yet made an advancement. With AlphaFold and the protein structures from AlphaFold, they were able to solve that particular protein in minutes. They've gone from years to minutes, really unblocking and accelerating that research. I think that is that alone is an incredible example of how AlphaFold is impacting in the world. There's another equally important example. There's a group working on developing malaria vaccines, a disease that devastates hundreds of thousands of lives every year. And they've been able to use these AlphaFold structure predictions for different proteins, but still AlphaFold structure predictions to speed up their research into malaria vaccines. So a couple of examples in healthcare, and there's other groups focused on neglected diseases where it may have been too expensive to do this the traditional way, but with AlphaFold predictions, they're making advancements. A slightly different example, but I think equally important and quite cool, is there is a group at the Centre for Enzyme Innovation, which I think is a university here in the UK, which is focused on developing enzymes that can eat the plastics eat the plastics that clog up our landfills and our oceans. And they've been able to use these protein structure predictions to speed up their work into producing plastic-eating enzymes. So we've got like, and those are just a kind of sampling of the different ways that AlphaFold's being used today. It's quite difficult to keep up. There's a kind of new group almost every week coming up with a way of using these predictions in their work.
Yeah, that's wild. So as AlphaFold applications expand, I mean, as Google comes up with more, programs like this, does it change the nature of Google's business? I mean, AlphaFold and Google Search are very different. So talk a little bit about how that fits together.
Yeah, it's a good point. These two things are quite different. And AlphaFold is a good example here of I described some of the ways that is having impact in the world. When I looked at AlphaFold, to your point, I was like, well, how does this work with Google Search? It's not obvious, right? How do these two things knit together? What's the match there? So I took a step back with my team and thought about other ways we could employ and deploy this. And it seemed we looked across a range of different areas and business opportunities, by the way, from agriculture to all sorts of areas. But in the end, we concluded that actually there is a great opportunity here in drug discovery. It takes 10 plus years to develop a drug. And then often when it goes into clinical trials, it fails. There's a very, very high failure rate. And so you've spent all that time and money and investment, and it doesn't actually make it through and solve the clinical need you're concerned about. So having understood this kind of scale and importance of the problem and the opportunity, that then gave us the impetus to form a new company. So we formed a new company, which is a sister company now to Google DeepMind. It's part of the overall Alphabet group. It's called Isomorphic Labs. It's about 2 years old. And its mission is to use AI to reimagine drug discovery. And the team is making fantastic progress. I'm really excited to see how that work will help reimagine that whole process. Now, there's definitely more research to do there. That's not just kind of AlphaFold and done. There are kind of AlphaFold scale problems along the way. But that's a really good example of where we've been able to set up something new based on a breakthrough like AlphaFold. And I think there could be other advances that come in science that may trigger a similar sort of arrangement.
So then does Google just become like an incubator for AI companies? Or, I mean, what is the nature of Google again, if it's like, can it just keep existing across all these different business lines?
I'm not well placed necessarily to talk about the overall corporate strategy for Google,
right.
But in terms of,
it's interesting because it gets into so many different areas. Yeah.
I mean, in terms of how I think about it, what's important for me to be doing is really focusing on the most important problems that Google has and the rest of the Alphabet companies, and making sure we're building and developing AI systems that can help solve those. And being alert, by the way, like the Isomorphic Labs example, when there is something that's important and significant and material enough, that I'm also surfacing that and saying, hey, do you know what? I think there's a really important opportunity in business here. Let's talk about it.
Yeah. Interesting. Okay. 5 minutes left. Self-driving cars. I'm in San Francisco right now here for a visit and hopped in a Waymo a week ago. And it was unbelievable. I mean, the way that these cars can drive around and no driver, it feels totally safe. I mean, maybe that's misplaced confidence, but it drove really well. How close are we to having these type of cars on the streets everywhere? And is it really a matter of needing more breakthroughs from the research side, or is it just a business? Will, I feel like you're perfectly placed to answer that one.
Yeah, well, I don't know. That's tricky for me because I'm not inside the Waymo business, so I'm not necessarily able to forecast or predict exactly where Waymo goes next. I've also had a ride on one of the cars, and it was about 5 or 6 years ago now. So, and my ride was pretty good back then, actually. So I'd like to have another go just to help calibrate myself on, I guess, the speed of progress, and that would help me predict where we're heading in the future. I'm here in the UK, so Waymo hasn't kind of made it to the UK yet, but I'm looking forward to have a ride then. So yeah, I'm not sure about exactly a Waymo, but I'm looking forward to monitoring and tracking and celebrating their progress for sure.
And from a research perspective, I mean, it seems like again, maybe you're not on the ground, so you can't share this, but from a research perspective, it seems like that should be solved at this point. I mean, I guess if they're already on the ground.
Yeah, as you said, I'm not on the ground with Waymo, so I'm not exactly sure where their research programs are. You know, they've got a lot of smart people at Waymo.
Let's end with this. We just had a year where people have been going bananas over large language models. I got a question today when I mentioned I was going to be interviewing you. People want to know, what is the next model breakthrough that's not an LLM, that people aren't paying attention to, but will be as impactful as what we've seen with these models?
I'm really excited. I don't know exactly what the breakthrough will be, but I'm really excited about the union of these LLMs plus reinforcement learning. And I'm excited about that because I think there's a lot more to come from reinforcement learning. And I know at Google DeepMind we have a great deal of expertise in that. So I expect to see the fusion of those two things create some really powerful and important breakthroughs.
Colin Murdoch, thanks so much for joining.
You're welcome. Great to be here.
All right. Thanks, everybody, for listening. Thank you, Nate Gwatney, for handling the audio, LinkedIn for having me as part of your podcast network, and all of you, the listeners. Great to have this conversation with Colin here for you. Hope you've enjoyed, and we'll see you next time on Big Technology Podcast.